All right, and then our final talk, I'm going to invite Ekaterina to talk to us about the very first NASA AI/ML crowdsourcing challenge results using SOHO LASCO data. Ekaterina, you're online anyway, I see you, but we don't see or hear you just yet.
Well, I'm here and I'm trying to open the file.
Okay, well,
So
we've been...
you have a copy, you know, because I have this, I think I have a lot of,
Just checking here.
so I think I sent a file and I think you should have it because I'm trying to open it and it's not opening here.
Is it something like this? Yeah, that looks better, right? And then, okay, yeah. So again, I'll give you a warning at 5 minutes and in your own time.
Thank you so much. Thank you very much for giving me this opportunity to talk here and present this. I think it's very unique experience using NASA SOHO LASCO data and building some project with crowdsourcing community. And I'd like to share with you my experiences and the results. So next slide, please. So today I will show you. Today I present you my experience. First, I start working with Amazon Web Service, and I'll show you results what I got working with them. And then I show you the results working with Topcoder because it was ultimately the winner to running this challenge on a crowdsourcing platform. And at the end, I'd like to share with you my experiences and kind of advantages and challenges working with challenges and what they can potentially bring into heliophysics. So next slide, please. So today I will address SOHO LASCO 2 data and all research done with using AI/ML approaches. And it addresses comets, finding comets in SOHO LASCO data. Next slide, please. So before I go too deep into this science and so on, I'd like to show you how data looks, you know, what's really the caveat here. If you look in this image on the left, it shows you distribution on comets. By the way, interestingly enough, about half of the comets found by SOHO LASCO imagery and not by ground-based observations. So I found this fact fascinating itself. And there are 6 different groups of the comets that were found with SOHO. And you see here distribution of brightness, different comets in each category. And as you can see, green shows you brightest comets, and there are not very many of them. Orange shows you medium size, medium brightness comets, and blue is faint category. So the total of more than 35,000 images presents more than 3,000 comets now. And so as you can see, basically there are slightly more comets, faint comets than any others in this imagery. And also very interesting that these data were collected by citizen scientists over 25 years for SOHO Life. And Carl Button, he is at NRL. He runs this project right now. He collected this data and this image. He provided this image. So next slide, please. So to to give you more idea of how comets looked in SOHO data, I show here imaging for magnitude higher than 5, magnitude between 5 and 8, medium brightness, and faint ones less than 8. It's really in a kind of limit of the instrument. And unless your eye is really trained, it's really hard to distinguish between background and see the comet. And could you please run me the movie on the right? This movie was created as a result of my work with Amazon Web Services, and it shows how they build, overlap over union model that trace bright comets in SOHO data. So this experience working with Amazon Web Services was very interesting in a way because they're really experts in the area of AI/ML. And it was very interesting to see how far they can go. And this is after working on a project for several months. They developed model that relatively good to trace bright comets without any other supporting things. So note that right now, until now, people were able to identify comets just using their eyes and brain, basically. Okay, next slide, please. So as a next step, I have this wonderful opportunity to apply. It's called at NASA Open Science Project that allows to submit different projects and kind of go through the competition process and see how it works. So basically, I applied this project through NASA at Work, and there all overall it was 14 ideas submitted, and 2 ideas was funded. Here are the links. You can read more about this open science initiative. And basically, a lot of challenges go through earth science. And the idea of this competition was to use NASA data and to address cross-disciplinary research. So through this opportunity, I was able to continue with this idea of trying to find faint comets in the SOHO data in a different way. And this is what I will tell you more later. Okay, go next slide, please. So the objective of this project was to build AML-based approach and to identify faintest noise level comets by reducing background noise in SOHO data. And it's very reasonable project because SOHO continues finding 10-20 comets per year. And basically, even people build their codes, they can be tested and validated one contents test with new set of comets. And so from this hub of NASA at Work, they have contracted companies, and our winner was Topcoder. And they developed platform to run challenge for ideation. And and they run marathon match to develop AI/ML-based algorithms. And a little bit on the background of this company. It has the largest network of designers, developers, data scientists from 190 countries. Basically, it's 1.5 million of these registered people. And the top coder history has 95% of success. So next slide, please. So there is a huge team who really worked on this project. It's not only me. It's a lot of people. So I have absolutely unique opportunity working with people who have absolutely a fantastic experience working with the data in heliophysics community, like Carl. But I also worked with people from completely different and new community to heliophysics. These people were from LISH, Laboratory for Innovative Science at Harvard. They're really cool experts in the area of how to build scoring, how to, work with the data. So we had two consultants from them. We also worked with data science subject matter expert. He organizes all these challenges in a large platform. As you can see, this platform can go up to 1.5 million people. So, and I can tell it that the way how these people work with data is completely different. What we deal right now in heliophysics. And it was really a breathtaking experience, how they think, how they organize data. It really should be really very generalized, very easy described for people who absolutely have no experience working with heliophysics data. However, there are really subject matter experts in area of artificial intelligence. And a couple of other people were from top coder managers, and the project coordinator was at Johnson Space Center. It's Steve Rader and Karen DeMilla. So I had a really big pleasure working with these people. Thank you. And next slide, please. So this is how we organized the data for this challenge. We used 39 gigabyte of data that contain comments, and we kind of inserted the 24 gigabyte additional data with empty data sets, we thought. And so basically to create this artificial data set for this specific challenge. And in our challenge, we had at that moment, we have more than 3,000 comments with among 36,000 images. So the data was separated into folders. In each folder, each folder contained FITS format file data and plain text file containing positional information. And you see examples here. Okay, next slide, please. So what we really asked crowd for, and believe me, it was really difficult process. It took us some time to kind of understand different languages between different even AI/ML communities in heliophysics, top coder and LISH. And so this is our final kind of wrap up on how we place it. We definitely wanted to do everything on a Python, so whatever will be product of this competition will be available and can be usable for free by everyone. So it was run on AWS platform. The output should come as CSV files, and output should include AI XY and real values in range from 0 1024, representing coordinates of the center of detected comet on the given image. And the output must contain no more than 5,000 lines. The same image not appear more than once in the same line.
Sorry to interrupt, Ekaterina. I got caught up in changing the slides. You have 2 minutes left.
Okay, so so can we go to the next slide then? So this briefly shows you how we organize it. We time-wise what and when we did, and you can see that this competition took just several months with the results at the end and discussion. So next slide, please. So as notable statistics, we have about 600 people registered for this competition from 74 countries, and we distributed 29,000 of prizes, and 3 main winners were from US and Belarus. Okay, next slide, please. So this shows you level of competition among participants, and red is the strongest one. We have only in this particular competition, we have people from yellow range. That basically means there were previously winners, but not necessarily many times. Next slide, please. This shows you how we trace this score. We develop scoring for this particular challenge, and it shows you how scoring changed over time. Our highest score was 100 and high achieved score was 67. Let's go next slide. So it shows, the next slide shows you facts of our winners that that people used in this, finding best solutions. One of them was algorithmic approach, and you see it was really fast, and the score was 66. And next solution was using. So can I finish with previous one? And it's probably also the next solution was a 3-part machine learning approach, and the last one was deep learning approach, which was more time consuming, but most importantly, it doesn't use any data reduction, but it has a lot of training time. And next slide, please. So I will briefly say you that these all people were all, all highly professional people from many years of engineering experience or experience in physics, but none of them worked with SOHO data before. Next slide. One was the engineer. The second one was physics from Fermilab accelerator who worked with high energy beams, identifying particles. Let's go next slide. And next was a deep learning engineer. Okay, and the next slide. So the challenge results now available in a GitHub repository, and not only this people identified faint comets, they were able to identify 2 new comets in a data that existed before. And the next slide shows you the data. On the left, it's a comet, one comet discovered from cruise comet set.
I'll have to ask you to finish up here, Ekaterina, sorry.
Can you just show the movie and I finish on that? Okay, one movie and another movie. So basically, these 2 comets are found with using AML approaches.
Okay, brilliant. Thank you so much. Oh, look, here we are. Okay, well, thank you very much. Have we any questions online or in the room? I've one for you, maybe wondering, are you planning on writing a paper or anything that summarizes your experience of running this competition, more so than the individual methodologies themselves, but how would other people go about doing something themselves if they have their own idea they want to get a challenge involved in? Oh, you're muted. I think you're still muted on our end, Ekaterina.
Okay, yes, I'd like to put some report on that. Because this meeting is international, but we're definitely working on these aspects in the US. There is right now going a lot of efforts for decadal survey. So how we work, usually people, it should coming from the community, how they want to work and how they would like to proceed in the future. So, but yes, there's initiative existing right now at NASA, especially in earth science, and I think it would be very beneficial if it will be extended to heliophysics.
Brilliant, thank you. Nobody else in the room? And nothing online. So, okay, thank you so much for your talk. And again, thank you everybody else for their talks throughout the session.